You are about to see the official film report of Operation Greenhouse. Greenhouse was one of a series of tests conducted at the Atomic Energy Commission's proving ground at Eniwetok. It was completed in the spring of 1951. Greenhouse was routine in one sense, but should not be confused with previous tests. Greenhouse has a place distinct and apart. While Crossroads tested the effects of atomic bombs and Sandstone concentrated on weapon improvement studies, Greenhouse was planned to further both of these achievements and more. Specific purposes of Operation Greenhouse, now accomplished, stand out. A, lighter, and smaller, and more efficient weapons for our atomic arsenal. B, offensive and defensive effects information on animals, structures, aircraft, tanks, and so forth. C, basic experiments of the thermonuclear problem. We believe this film to be a true presentation of the operation. It stresses underlying themes, the reasons for Greenhouse. It cannot always give credit to the thousands of individuals who made it possible. As commander of Joint Task Force 3, I invite you to see a documentary portrayal of an operation which many agencies and unnumbered men achieved in the Central Pacific, an atomic test.
It's all over now. Only the radioactive dust of the 4 test shots remains. Operation Greenhouse is history. But if this be history, what does it say? What was learned from the shots fired at Runit, at Engebi, at Eberiru in the spring of 1951? What was done to warrant the expenditure of thousands of man-hours of work, of millions of dollars? Just what significance does Greenhouse have in the gallery of atomic tests? Operation Greenhouse, Joint Task Force 3, starts like a puzzle with 1,000 scattered pieces. One of these pieces fits into place at 12th and Constitution, Washington, D.C. This is headquarters for Joint Task Force 3. Here, during the greater part of 1950, activity centers around complex organizational problems. This is the clearinghouse, the meeting place, where both the services and the scientists work out mutual problems. Here, men come to grips with the 1,000,001 details connected with an operation of the magnitude of Greenhouse. Details that can become as wearisome and heavy as an aching tooth, but which also cannot be ignored. Consider just one item, transportation, docks and ships, airfields and planes, plotted on sheets of paper, on schedule. 14 to 15,000 tons per month by water, outward bound from San Francisco, 5 days to Hawaii, 6 days to Eniwetok. Transportation for normal cargo or high priority cargo. Transportation by air, 7,300 passengers, 940 tons of freight from the United States to Kwajalein, to Eniwetok. Yes, planning, organization, phasing, detail. The story of headquarters, Joint Task Force 3, during these hectic preparatory days is a story of the valuable function of support. Support, a part of the how of Greenhouse, but not the why. The why of Greenhouse starts in the summer of 1948. Starts at Los Alamos, New Mexico. Begins in this, an isolated experimental factory set up for a specific purpose, to design and develop atomic weapons. In the shadow of the Jemez Mountains, work progresses steadily, as it has from the laboratory's beginning in 1943. Since then, to the summer of 1948, men from this plateau have left this country twice before to test the weapons they have created. Go ahead, Los Alamos.
We return to the Hill from the Sandstone tests with new and important information. Information that would enable us to make a sizable contribution to the generally rising curve of man's knowledge of atomic weapons. Information that would help us tackle basic problems involved in high explosive systems, pit designs, core arrangements, initiators. Information that would enable us to increase the small percentage of active material that actually burns during fission. The more efficient use of fissionable material has been and continues to be one of our main objectives. For it is the fissile material itself, whether uranium-235 or plutonium, that is the expensive, the elaborately complicated material to produce. The nuclear material is the heart of all our attempts to make bombs economically feasible. At Trinity in 1945, we proved a self-sustaining reaction could become an explosive force, and that the implosion principle was sound. We had a starting point. The drops on Japan were strictly a war measure. At Hiroshima, we tried the gun principle and also used uranium for the first time. The Nagasaki weapon was an implosion type using plutonium. Little or no controlled experimentation was possible. Thus, little data was obtained which furthered the progress of weapon design. As a result of the Japan detonations, the effects from an atomic explosion became of prime concern to the armed forces. Thus, Crossroads with its two plutonium-type weapons, both using an implosion system. At Crossroads, since we were mainly interested in testing naval materiel, little data was obtained from the Able and Baker shots on weapon development. However, significant effects knowledge was obtained. Stateside laboratory research, in the meantime, developed new weapons for the Sandstone tests. At Sandstone, we were once again able to tackle the big problem, more efficient use of fissile material. Here, we were able to utilize uranium-235 in an implosion-type weapon. So, as time went on, we had increased our knowledge of weapon design and had, therefore, increased yield per kilogram of active material. This is where we stood by the end of Sandstone. But, while this was satisfying progress, new possibilities already loomed on the horizon. Even while still unpacking our suitcases from the Sandstone tests, thinking was in order for the next operation, for a new test program, Greenhouse. It is apparent that controlled testing, such as that at Trinity and Sandstone, is essential for continued progress in the development of atomic weapons. It is equally obvious that testing at a proving ground is to be a permanent feature of our work. So a proof test division, known as J Division, is organized. Dr. Alvin C. Graves is selected to head this division, a unit with the specific job of testing weapons. By autumn of '48, a test program is framed. This calls for experimentation of new weapon designs with the objective of again moving our knowledge curve upward to a more effective level. Operation Greenhouse, a logical sequence to Sandstone, is in the making. Once more, we propose to better yield per kilogram invested. Greenhouse may take us a long way in the direction of smaller weapons. For the first time, deliverability in terms of size and weight is expected to make its mark in improved weapon design. Greenhouse will also give us direction as to what road to follow in the development of a thermonuclear weapon.
This is the beginning, the first step in the long road to make Greenhouse a reality. It is desirable to obtain an early approval of the test programs, for a major lesson had been learned from Sandstone. Thus, time is an essential ingredient. Time for preparation, time for organization. With time, the most value for a given dollar spent will be accomplished. Besides, time to prepare for active participation is indispensable to the military services.
We in the services received the announcement of the proposed 51 tests with high interest. There were many tests we hadn't had an opportunity to run during Operation Sandstone. As a result, there were gaping holes in our offensive and defensive thinking about atomic weapons. Naturally, then, we were anxious to conduct experiments in an operation such as Greenhouse. At first, each service worked out its own program separately. Working independently in this way, there was overlapping and duplication. Later, we began to condense our tests into a unified, workable program after we had met with AEC scientists and understood more about the test shots and the limitations facing us.
And so, while the play is being written, the actors selected, the Military Liaison Committee recommends to the Joint Chiefs of Staff that now the time is right to tie all the loose ends together. To start the ball rolling, General Quesada is nominated as Task Force Commander and heads a temporary Joint Proof Test Committee. This committee functions for some 5 months. Based largely on experience gained from Operation Sandstone, it develops the basic plan for Greenhouse. The Proof Test Committee gradually merges, gathering members into a full-fledged unit, Joint Task Force 3, a unit operational by November 1949. This task force is an organization made up of 4 integrated parts, 4 task groups. Thus, Task Force 3 for Greenhouse reaches an objective not entirely realized in Sandstone. This is a true quadrilateral unit in which each task group is assigned the job for which it is best suited. The aim is functional efficiency rather than service interest.
In essence, the mission of the Scientific Task Group is to prepare, arm, and fire the test weapons, to conduct the experimental programs for the Atomic Energy Commission and the Department of Defense, and to operate and maintain the necessary base and laboratory facilities for conducting experiments.
The Army Task Group will provide the necessary men and equipment to rehabilitate Eniwetok Island, and will continue to operate and maintain the island during the operational period. In addition, the Army will operate port facilities and ensure the physical security of the atoll.
The Navy Task Group is charged with the responsibility of maintaining surface security over the Eniwetok danger area. It will transport the experimental weapons and provide assembly facilities. The Navy will provide logistic support for the operation and augment facilities for intra-atoll water transportation.
The Air Force Task Group will provide and operate aircraft necessary for the experimental programs and the airbase facilities necessary to maintain these aircraft. It will assist the Scientific Task Group in collecting test data. Also, it will maintain a continuous display on the air situation, operate search and rescue activity, and provide documentary film coverage.
4 task groups, representing civilian and military personnel, now work together as a unified team, as a task force. Eniwetok Atoll, the proving ground, established as a permanent site for firing atomic weapons. Since this atoll had been used in the 1948 tests, there were some buildings, living facilities, and test installations available. But 2 years have passed. Repair is needed. Expansion is necessary. Cleanup, construction, and maintenance on all islands of the atoll, except Eniwetok Island, is handled by the civilian engineering firm of Holmes and Narver in Los Angeles. The first step of their engineers is to get a clear picture of the requirements, to make a survey. And while in the far Pacific the isolated proving ground is being prepared, in other parts of the world, events occur which give added significance to and have a profound effect on the planning for Operation Greenhouse. A hydrogen bomb, a fusion bomb, a thermonuclear weapon, call it what you will, the moment for decision arrives. The world situation offers no other choice but to push the development of this type atomic weapon.
A thermonuclear reaction. We know the reactions on the sun are of this kind, probably the slow fusion of hydrogen taking place over millions of years. Our problem is also to produce a fusion reaction, but that is as far as the similarity with the sun goes. We can't wait a million years. Ours must be here and now and explosive. A tall order, But because of the urgent need to know if a man-made thermonuclear reaction is possible, we are going to burn the midnight oil until we have an answer. By now, we know the blueprint for mass and energy. We know how to cause the splitting or fission of heavy atoms to produce an explosive chain reaction in the case of uranium and plutonium. When fission occurs, the total mass of the two fragments is less than that of the original mass. That difference is energy. Fusion, as the term implies, is a fusing together of two atoms into a single nuclear unit, the direct opposite of fission. But still, for light atoms, the new mass is less than the combined masses of the original atoms. The difference, again, is energy. However, energy from fusion weapons, theoretically at least, is unlimited. Unlike the critical mass limitations of uranium and plutonium, any given amount of active fusible material can be assembled to produce an explosive force. All this is true if a suitable material is available. Ordinary hydrogen, the common element used so frequently and inexpensively, fuses and produces energy on the sun. But on Earth, ordinary hydrogen atoms do not easily fuse. Simple hydrogen is definitely not suitable as a thermonuclear fuel, but it is believed rare forms of hydrogen will work. So, one of our first problems is to experiment with an isotope or isotopes of hydrogen. Work with materials capable of undergoing an ignitable, self-sustaining nuclear reaction. If we can prove that it is possible to achieve a self-sustaining nuclear fusion reaction in a small quantity of material, we will have a starting point. We're going to try to be ready to attempt the test of a measurable thermonuclear reaction in a little over a year on Operation Greenhouse.
Not only is work intensified at Los Alamos and many other labs and installations in the United States, but also in Eniwetok Atoll, engineering work is rushed to make possible the test by the spring of 1951. Construction starts from the ground up and grows into a proving ground. While work progresses in the Pacific, preparations keep pace in the ZI. Preparations based on 8 experimental programs.
Program 1, Los Alamos Tests, designed to obtain answers to several key questions relating to the national stockpile of fission weapons, to effects which nuclear weapons are capable of producing, and to possibilities in the direction of thermonuclear weapons.
Program 2, Biomedical, sponsored by the Atomic Energy Commission and the Department of Defense. It will consist of the measurement and recording of the effects of the atomic explosion on animal and plant tissues.
Program 3, sponsored by the 3 services. The response of various types of buildings to the atomic explosion will be measured and analyzed and will provide a test of various types of blast-resistant construction.
Program 4, Cloud Physics, sponsored by the Air Force, will consist of the measurement of physical phenomenon accompanying the cloud which is formed after the atomic explosion.
Program 5, Radiological Instrument Evaluation, is sponsored by the Army and Navy. Its object is to evaluate equipment which has been designed by the services for use in detecting the radiation produced in an atomic explosion.
Program 6, Physical Tests and Measurements, will consist of 10 separate projects to determine the effects of atomic explosions on various kinds of military equipment and the effectiveness of decontamination methods.
Program 7, an Air Force project to determine the effectiveness of detecting atomic explosions at long range. This project is widely dispersed. By JCS decision, JTF-3 was responsible for only that small portion of the program conducted at Eniwetok. Therefore, this film does not include details of Program 7.
Program 8, Effects on Aircraft, will measure and record the effects of the atomic explosion on aircraft in flight and on certain airplane components on the ground.
While all over the country men work to make Greenhouse a reality, during this preparatory stage, new events of world importance occur, which cast their shadow on the operation. However, national policy dictates that the vital atomic test program must be maintained, that weapons development work must continue at any cost. True, some schedules are altered, some drawings revised, in order to still make Greenhouse a reality in the spring of 1951. But actually, a shift in plans is not strange to those who work on this operation. Modifications have happened before, and they'll happen again. Since Greenhouse is a remote outdoor laboratory situation, a series of experiments, change will be the order of the day, up to and including the actual operational period. Even during test time, Holmes and Narver will have a small working force available to make last-minute installation changes. So, work continues in the ZI at an accelerated pitch until at last the time arrives when most plans can be laid away, blueprints rolled up and put in drawers, instruments, gauges, meters, packed for the big move out to the Pacific Test Islands. The Scientific Task Group will control the experimental program, but the largeness of the total project means that individual experiments have been farmed out to dozens of different bureaus, laboratories, institutes, offices.
Some of us had never seen Eniwetok Atoll before. We had studied charts, of course, but we were more interested in the real thing, especially in the headquarters islands and the test islands. Eniwetok Island is headquarters for the Army and Air Force task groups. Perry Island is headquarters for Joint Task Force 3 and for the Scientific Task Group. This operation, unlike Sandstone, is land-based. Headquarters for the Navy Task Group is aboard the Curtis, anchored in Eniwetok Lagoon. Moving north up the chain, Runnet is the site of the first shot, codenamed Dog. Still moving north, Ibariru Island is the location for the third shot, codenamed George. Engebi is at the top of the chain and is the test island for the second shot, codenamed Easy, and for a possible fourth shot, codenamed Item. Over this spread-out atoll laboratory and over the surrounding rectangular danger area 150 by 200 miles, the Navy patrols, maintaining a security watch.
The 5,000-mile trip from San Francisco to Eniwetok is over. We settled down in the tropical aluminum barracks that are to be our home for the next 5 months. There isn't much to do out in the islands but work, and there is plenty of that. Instrument footings, recording stations, coax cables, and the like are in, but this is just the beginning. All of the elaborate test instruments brought from the States must be installed.
But before Greenhouse came to this point, the actual operational period, before the test islands were set, before the exact weapons to be tested were chosen and dates settled on, many events of importance had influenced the aims and purposes of the 51 tests.
Okay, Fred, let's go ahead on that basis then. You'll have to check up with EG&G to see if they're set up for that sort of thing. Right. Okay, Fred. Well, what's your problem, Bowen? Isn't history being written fast enough?
I'm afraid too fast for me, Dr. Graves. I have trouble trying to keep up with it. In preparing the chapter on the selection of weapons for the Greenhouse report, I have difficulty in following through the historical development. I wonder if you could give me a summary of the changes.
I can understand your difficulty. Things have certainly changed often enough. First, let me discuss briefly this business of change, flexibility in our work. From our point of view, flexibility in testing is a necessity. If we were completely sure about our weapons, if everything were cut and dried, there wouldn't be much point in running a test such as Greenhouse. Being absolutely sure is a tall order, and being mere men, we're not infallible. Hence, we must anticipate program changes.
I can understand the necessity for change. It's the historical sequence that bothers me.
Well, now to outline the more important changes. After Sandstone, in the latter part of 1948 and 49, we were thinking in terms of a three-shot program.
Work starts at Runit, Zero Island, for the first test shot. The plan is to concentrate on one test shot at a time. So, effort now centers on this finger-shaped bit of coral soil. The 300-foot tower to hold the first test weapon is ready, as close to 7 April as will be feasible.
The Runit Tower is 100 feet higher than any tower used in a previous atomic test. This increased height will allow a better fireball to develop and therefore provide a better measurement of yield. This added height also cuts down ground dust, lessening fallout contamination.
Natural phenomenon is under continuous observation by the meteorologist. He closely watches earth and sky and sees much more than just heat or cold, wind or rain. For two reasons, weather is an important factor in every atomic test. First, a day must be picked when visibility is good for photographic records. Second, a day and time must be selected when wind and rain do not adversely affect radiological safety. Talk about a spread-out project. Weather units are all over the map. An aerial recon unit is based on Kwajalein. This unit is made up of 12 B-29s modified for weather reconnaissance work. They fly 3 triangular tracks every day out of Kwajalein and radio in weather information every 100 miles. Then there are 4 fixed weather task units on outlying islands at Kusai, Nauru, Majuro, and Bikati. Here is one of the stations, Majuro. On this self-contained outpost, the men make a surface observation every 3 hours. A complete upper air observation is made every 6 hours. In between these observations, they work on a cloud development study, which is part of the research on tropical meteorology. All of the weather data is funneled in here to Task Force Weather Central on Eniwetok Island. The job of the Central is to forecast weather for the day and hour of shot time. All effort now centers on job number 1.
Those of us from the scientific task group are here essentially to confirm or disprove theoretical calculations, to learn what is not always possible to prove in a conventional laboratory. To learn more about the atom bomb, we divide our testing into 2 major areas: diagnostic testing and effects testing. More specifically, diagnostic tests are an extensive examination of the phenomena occurring during the initial phases of the explosion. Effects tests study the external manifestations of the explosion, the effects of the weapon. To gain an intimate understanding of interior weapon behavior, 3 kinds of diagnostic measurements are made. These are the time it takes to start the nuclear reaction, transit time; the rate at which the chain reaction multiplies, alpha measurement; and measurements of the total energy released in the nuclear reaction, yield. Most of the diagnostic data is available only during the early microseconds of the nuclear reaction, and extensive instrumentation is required for each detonation. Transit time data, which gives information on the HE system, is cabled down to a recording station and measured by sweep oscilloscopes. Transit time instruments are wired into the same circuit that triggers the detonators of the weapon. Because they are activated by the same impulse, they can literally measure the duration of the implosion, or the time necessary to condense the nuclear material to criticality. Transit time is the interval, then, between the impulse and the appearance of the first gamma ray, which signals the beginning of the fission process. The oscilloscopes are extensively photographed during their microseconds of operation, since transit time is an important index of implosion efficiency and offers a good check of weapon design. The second phase of diagnostic experimentation, giving information on the internal workings of the core, is the alpha measurement. One way to obtain this data is to locate an ionization chamber adjacent to the weapon itself. Other ionization chambers, located at ground level, detect later stages of the alpha phenomena. Measurements of alpha give valuable information on the multiplying qualities of the fissionable assembly. The multiplication rate is vital. It tells us of the growth of fissions in a given length of time. If we are to have more efficient atomic weapons, we must increase the rate at which fissions multiply. As radiations from the fissions are detected, a signal is sent down the coaxial cable to a recording station. The rate of increase of signal strength is recorded by some of the fastest recording equipment in existence today. In addition to the transit time and alpha diagnostic experiments, we have several methods of detecting the success of new weapon designs in terms of yield. Yield is the determination of the total energy released by the nuclear material undergoing fission. This energy is usually expressed in kilotons. 1 kiloton being the energy released in 1,000 tons of high explosive. One means of measuring yield is to attach filter traps to drone aircraft and send them into the core of the atomic cloud immediately after the blast. Nuclear ashes or samples of the residue material saturating the cloud are collected in the traps for radiochemical analysis to determine the total number of fissions that have occurred. Since we know the yield per fission and measure the total number of fissions, the yield of the bomb can be computed. The SNAP sampler, a device new to atomic testing, is another way of collecting debris for radiochemical analysis. Samplers of the air type and samplers of the ground type are arranged in a semicircle close to the base of the tower. In addition to these methods of collecting samples of fission fragments, Greenhouse will test rockets for the first time to see if they are practical as sample collectors. The rockets will be fired just prior to shot time. They will travel in a long arc and pass through the cloud at approximately 5,000 feet. It is hoped that on the pass-through, they will collect samples in much the same way as drone aircraft. Another measure of yield is made with high-speed still and motion picture cameras, which record the rate of growth of the fireball. The more energy developed in the reaction, the faster it expands. To repeat, the diagnostic experiments are concerned with the behavior and phenomena of the weapon itself. However, we are also concerned with the 4 physical effects produced by a nuclear explosion: blast or pressure, heat or thermal radiation, light or visible radiation, and nuclear radiation in the form of neutrons and gamma rays. To measure the pressure of the blast on the ground, several types of instruments are arranged in a blast wall. A number of these blast walls, called collectively a blast line, are situated in a straight-line path to the shock wave. Each blast wall contains instruments to measure pressure as a function of distance and time. One excellent method of obtaining peak pressures at various distances is through the measurement of the velocity of the shock wave. Since high shock velocities are associated with higher pressures, blast or pressure of the weapon can be obtained. This type of instrumentation, on or near the ground, measures Mach region pressures, or the composite of the initial shock front and the reflected shock wave. For some time, we have been interested in free air pressures, that is, pressures not influenced by the reflected wave. We are attempting this free air measurement in a new way by suspending telemetering transmitters from plastic balloons inflated with helium. The balloon and its cable ride close to the tower at an altitude of about 2,000 feet. As the shock front strikes the balloon-borne instruments, time of arrival signals are sent to a recording station on Perry Island. With such data, we hope we can determine effective height of burst for any type of atomic weapon. The amount and distribution of thermal energies emitted directly from the bomb and penetrating to a great distance will be determined. Information on the heat produced is of prime interest to both the scientist and the military, since thermal radiation is an extremely potent effect of an atomic explosion. The spectrum and intensity of light, or visible radiation, will be measured by high-speed spectrographs and photocells, and the fireball will be photographed from 100 to several million frames per second. The fourth category of our effects testing is concerned with gamma and neutron radiation. The photographic neutron experiment, PHONEX, will enable us to learn more about all portions of the neutron spectrum. PHONEX converts neutrons to protons, which are recorded in a photographic emulsion. Additional data about neutron radiation will be obtained from threshold detectors. Samples of gold, sulfur, iodine, and other elements are attached to a land cable, which can later be hauled back to a safe recovery point. Such elements are made radioactive by neutrons above a threshold energy and again provide a measure of the number and energy of neutrons. Gamma radiation is observed in several fashions. Spectrometers placed at several distances will measure the energy spectrum of gamma radiation. At the same distances, the spatial distribution of the delayed gamma source is measured. At 4 locations, detectors will measure absolute gamma intensity versus time. In short, we want to know what kind, where, when, and how much delayed gamma radiation is present. These measurements are needed if we are to calculate the shielding properties of our shelters or to estimate the required shielding at a given distance. Thus, all effects measurements are made to help us in both civil defense and military planning.
Only one day over schedule. Now, in dramatic pre-dawn darkness, the drone aircraft are ready to take off on their missions. Giant planes without a living man on board, and with all their tons of weight and thousands of horsepower, flown by a remote control officer on the ground through an incredible gadget in his hands. On signal, the first safety crew abandons its drone. Comes now the fantastic achievement of a 4-motor bomber taken safely off into the air by those distant magic fingers, which then, with even mightier magic, switch the manless controls of the drone aircraft to a mother plane aloft. Each mother hovering impatiently to take its crewless baby on through the darkness, guiding it into the unknown. To top the fantasy of the crewless bombers come the fighters. For the first time in airplane history, drone jets, pilotless, crewless, at super speed flown up into the night sky, controlled only by a driver and overdriver in other jet aircraft who electronically guide the destinies of their jet drones.
The general location of all aircraft must be known for safety purposes, but the exact location of each blast measurement aircraft and filter collecting drone is an absolute must. And so the Air Operations Center takes over the meticulous task of advisement and control. This is the hub, the center of all 3.4 activity. Here in the center is maintained a continuous display of all air activity in the Eniwetok area. Air defense for the protection of this atomic proving ground, search and rescue operations. But the main concern of air operations is during shot time when test aircraft hold the center of the stage. Their critical flight paths are displayed on an air defense board, followed and checked and sometimes nursed to zero position at H hour. These drone ships are guided through the blast area by close support MSQ-1 units. Radar tracking, coupled with electronic computers, takes over control from the mother aircraft while the drone is in the blast area. All these plots are of sufficient accuracy and timeliness to permit the Air Task Group commander to make his report to the Task Force commander that all aircraft are in position and ready.
From many points outside the danger area, men now look to run it. The time has come. Shot number 1 is ready to be fired. One of the most impressive manifestations of any atomic blast is the cloud, containing the unburned particles of the reaction, the heavily radioactive nuclear ashes.
Opportunities to study an atomic cloud are rare. To learn more of its characteristics, a separate program, Cloud Physics, makes a detailed study of phenomena associated with it. While drone aircraft are used primarily to gather samples for radiochemical analysis of the cloud and to study blast effects on aircraft, we take full advantage of them in running additional experiments. Instruments in these aircraft automatically record air temperature, humidity, pressure, and airspeed. In addition, two B-50 aircraft, beside their regular mission of blast measurement, mount cameras which record the dimensions, rate of rise, and the diffusion of the cloud. This type information gives us better understanding of cloud construction and behavior. Such information would have particular importance in developing a warning system which would tell air crews when they are approaching a radioactive cloud, so that they may turn aside to avoid damaging radiation. The Cloud Physics program is also making a detailed study in wind measurement, to gain a more complete understanding of the structure of the negative wind or afterwind following the blast wave. Here we return to collect the records from one of our wind measuring devices. Altogether, there are 27 such instruments located at varying distances from point zero. All of the studies under the Cloud Physics program will help contribute to a better understanding of the aftermath phenomena of an atomic blast.
Drone planes. Practically every one of the 8 programs has some test gadget in, or out of, or hanging on to this remotely controlled guinea pig. As soon as each shot is completed, the task of compiling and computing test data moves into high gear. Some of the test measurements, as for instance the Los Alamos filter trap samples, need to be quickly shipped back to the laboratories in the States. An airlift, the Pony Express, is in operation for just this purpose. Dwarfed by the C-54s, the small liaison planes are another kind of airlift. They are island hoppers, transporting personnel around the scattered facilities of this proving ground. At first, traffic was heavy to run it. Now it concentrates on Engebi, Zero Island for test shot number 2. Preparations for this shot are going on up and down the atoll. For instance, on the way up to Engebi, you pass a small island near Parry. Interesting events are occurring on this heavily vegetated island, seemingly tranquil and forgotten in the midst of all the turmoil.
This is the island home of some 200 dogs, 200 pigs, and a mere 12,000 mice. This is Japtan Island, headquarters for Biomedical, Program 2. And this also is our home. While we work with complicated instruments, gauges, and chambers, our main instruments are simply animals. We started here nearly a year ago. We brought in parent animals so their young would be native-born, completely acclimated animals. This method helps us avoid alien environmental influences. Control, as in most of the sciences, is the thing we work hard to attain. And control is the principal reason why mice, pigs, and dogs are being used. They are standard laboratory animals we've worked with for years. It's possible to highly inbreed them and produce beasts of the purest blood strains. This means control, or accurate results. Yes, we've been here for months now. The young have grown up and are ready to help us gain valuable information and facts on the treatment of human casualties in case of an atomic war. A few hours before zero time, we will gather up our animals and move them into position for the Engebi blast.
The bulk of the $10 million military effects programs are centered around the Engebi shot. On both Engebi and Musen Islands, for example, stand the products of Program 3, structures. Some appear strange, others familiar. Some are exposed, others hidden. A joint military test program to gain offensive and defensive knowledge of structural reactions to an atomic blast. Important information for the protection of our cities. Important information for the destruction of enemy cities. Army structures. A multi-story composite building, 7 separate sections arranged to respond independently, located 990 yards from zero. We are after this kind of information. Are our design criteria adequate to our needs? How do various types of construction respond? What are the effects of window openings? Blast-resistant shelters, 570 yards from zero. Built of reinforced concrete, 1 cubical in shape, 1 cylindrical in shape. Here we are after defensive facts. Navy structures, bomb-proof roofs, 60 yards from zero. A solid reinforced concrete roof, 5 feet thick. A 4-layer laminated roof. We have already successfully tested this for penetration by TNT bombs. Will it stand up to a fission bomb? Other Navy structures, a powder magazine 1,170 yards from zero. A concrete arch. We ask another question. What is the effect of a curved surface to atomic blast? And still another question. What blast protection will panel veneer provide? In all of this, the Navy is after defensive information. Air Force structures, an industrial building with long spans. A building representative of possible targets in such industries as aircraft assembly. Close by is a scale model of the same type structure. This is representative of an attempt to gain an understanding of atomic blasts on structures by using cheaper scale models. A short span industrial building, representing a light manufacturing plant. A 2-story brick building, a structure representative of urban dwellings in many cities. The Air Force is mainly interested in offensive data, height of burst, number of bombs, 0 point, all to ensure maximum results on a target.
Program 6, Physical Tests and Measurements. Generally, you might say ours is a defensive program.
We're trying to find out the best ways of protecting ourselves and our military equipment from an atomic detonation. Take tanks, for instance. What effect does blast have on armor and armament? What pressure is built up inside a tank? What is the temperature inside? What is the effect of radiation at various distances on crew members? And can they continue to fight? To answer such questions, we have placed Sherman tanks at 500, 750, and 1,500 yards from zero and instrumented them. And then we would like to know something about thermal radiation, the heat in light, and the effect of such heat at various distances upon items such as woods, paints, plastics. Another point, we're not satisfied with our knowledge of the fallout of atomic particles over a wide area. These glass collector plates coated with Vaseline will be placed on 9 islands of the atoll to gather samples. Filter materials must be tested to check their efficiency for gas masks, large air filters, and the like. All of these and many more questions to be answered. Important questions for military preparedness. Important data for civilian protection.
Although the Air Force has dropped live bombs on targets, actually little is known about the reaction of striking aircraft to atomic blasts. It is the purpose of Program 8, Effects on Aircraft, to gather more controlled data on the tactical employment of bombing aircraft, and also to find the modifications necessary to the structural design of present and future airplanes. These tests will take place in the air and on the ground. For the ground test program, we are setting up aircraft components in the path of the blast. At 4 stations placed at various distances from zero are such items as vented cylinders, an F-47 wing with vented flaps and ailerons, wing panels, an F-80 fuselage. Each site has an instrument station loaded with recorders, strain gauges, pressure, and temperature sensing devices. Down on Eniwetok, the blast measurement aircraft are being readied for tests in the air. 2 manned B-50s and a manned B-47 will traverse the blast at high altitudes. Drone aircraft will encounter the blast at lower altitudes. 2 B-17s and 2 T-33 jets are assigned for this purpose. To measure and record the stresses and strains of an airplane hit by an atomic blast, all planes are heavily instrumented. Since one or more of the drones might not survive the blast, key information will be telemetered down to the recorders on Eniwetok.
And so, as time passes quickly, the programs on Engebi are ready.
At Japtan, the months of planning and preparation draw to a close. Our time has arrived. With the approach of H-hour, we put our test animals into exposure containers to make it possible to quickly establish the numerous stations before detonation and to efficiently collect them after blast. Trucks equipped with a hoist mechanism for quick loading and unloading techniques carry our living laboratory specimens to the waiting boat. While much information has been gained from the 2 detonations on Japan and from previous atomic tests, this material lacks the all-important factor of cause and effect, which is indispensable to medical knowledge. Our present program is designed to supply the missing facts. Then we are on our way, moving up with our mice, pigs, and dogs. At minus 18 hours, we're ashore on Zero Island to test casualty production, heat, and radioactivity from a full-scale atomic blast. Time becomes an all-important factor now. We are dealing with live animals here, beings who can go only so long without food and water. Mice will be spotted to determine lethal radiation dosage. They will be spaced at varying distances from zero, so that the dosage received will range from several times lethality to non-lethality. Pigs are the basis for an interesting experiment. Since pig skin is similar to human skin, these animals will give us important information on thermal burns. To make certain we get this kind of data, the pigs must be anesthetized to keep them in position. This special station protects the pigs from blast and nuclear radiation, leaving the way open for our study of thermal radiation. During the explosion, a shutter, like a camera shutter, will travel across the cage opening to give information on the time of burning. This will enable our scientists to make a full-range study of thermal burns at varying distances from zero. Filters are also used to determine whether ultraviolet, visible, or infrared causes the burns. Well, our job is over for the present. Now all we can do is wait. Wait and hope that what we learn here will make invaluable contributions to pure science.
Now it is the night before the second shot. Flash and fire of number 2 shot is history. But the facts to be learned from it are still in the present. Roughly 20 minutes or so after shot time, men approach Zero Island. Radiological people, men with beta gamma counters to measure Röntgens and decide and declare what is safe. Biomedical people, anxious to set foot on the island, for they must get in as soon as possible to retrieve their test animals. These precious laboratory animals, representing the possible future story of human reactions to an atom bomb, are hurriedly gathered and sped away on trucks. Meanwhile, other men observe their instruments, make their studies.
The Navy, as well as the Army, feels the vital need for accurate radiological safety instruments. We are charged with the job of proving present RadSafe instruments adequate or proof testing new types, and to gain sufficient information to develop others to keep pace with the rapidly changing field of atomic energy. This, in essence, is our story of Program 5.
It can be said of radiological safety in general that radiation is not as great an unseen menace as once believed. Radiation is fairly well localized, as for instance near Easy Shot Zero Point. Once again, the men of Program 3 move in to look at their test structures. This is the after effect. Structures once so precisely arranged, so scientifically constructed, and so carefully instrumented, now are twisted, broken, and shattered. And strangely, some virtually remain untouched. From the shambles, technicians collect their findings, dig through rubble for precious instruments. Data will be collected from these and from high-speed photographic records. Special cameras that have recorded the collapse of a wall or the sudden shattering of a complete building. Combat vehicles are studied for the effects of blast, heat, and radiation. Clothing is gathered and sent to Eniwetok Island. Here, a mobile field laundry, operated by a specially trained quartermaster team, handles the contaminated clothing to determine the efficiency of decontamination methods. While the 1,001 studies continue, while the large and small conclusions of Shot 2 are being drawn, preparations are already underway for Shot 3. Test shot number 3, the thermonuclear experiment. Now, Eniwetok 1951, like Alamogordo 1945, becomes a laboratory devoted to a basic premise in nuclear physics. This time, the object is to prove that a self-sustaining fusion reaction is possible. This will be the first attempt to produce such a fusion or thermonuclear reaction on this Earth. It may well lead to a new departure in the applications of nuclear reactions to warfare.
Our test setup for the thermonuclear experiment appears complex. From the beginning, however, the idea was to make our first experiment as simple as possible. To state the basic plan, thermal energies from a fission reaction would be focused on a trace quantity of fusel material. Measurements of this fusion reaction would give information necessary for further experimentation. It is still not known whether the heat generated lasts for a long enough period to be usable. This is one of the questions to be answered. Another major factor in the development of a thermonuclear weapon is to find out whether fusion can be made self-sustaining. We're counting on the fuel we use for this test to give us the answers. We have selected a combination of the hydrogen isotopes deuterium and tritium. Deuterium is obtained by relatively simple chemical means, while tritium is pile-produced, a complex and costly process. Deuterium alone is far and away the most practical fuel. However, there is considerable question regarding its reaction time, its ability to ignite during the fraction of a microsecond that the required degree of heat is available. At the present time, however, we don't believe that tritium atoms will fuse with each other. On the other hand, our studies indicate a reasonable probability that tritium will fuse quite readily with deuterium. A mixture of the two, then, a DT mixture, stands a chance of successfully reacting. This is called the X-ray experiment, since very hot materials emit soft X-rays. The data is transmitted by coaxial cable to a recording station. Inside the thick walls of the recording station, oscilloscopes receive and record the data in the fraction of a second before the tower and all the instruments are consumed in the explosion. Another measurement of the thermonuclear reaction is the diagnostic neutron experiment, called DYNEX for short. When the deuterium-tritium reaction occurs, a high-energy neutron is left over. We have calculated that this neutron will have an energy of approximately 14 million electron volts. As the reaction goes through the DT compound, there is a rapid increase in the number of neutrons emitted. If the thermonuclear reaction occurs with reasonable efficiency, a substantial quantity of 14 MeV neutrons will be given off. Since in a normal fission reaction there are only a small number of 14 MeV neutrons emitted, the fusion reaction will appear as a sharp upswing from the normal fission curve. If this type curve appears, the thermonuclear reaction will be a reality. DYNEX is the experiment designed to obtain this curve. Most of the facilities for the DYNEX experiment are in the tower. The detecting instrument itself is surrounded by a lead coffin. The coffin, in turn, is entirely surrounded by water in a steel tank. The object of all this shielding is to filter out all unwanted products of both the fission and fusion reactions, and permit only the 14 MeV neutrons to reach the detecting instrument. 14 MeV neutrons will pass through a collimator and through a lead window which filters out neutrons of a lower energy level and permits the 14 MeV neutrons to lodge in a paraffin-like material. The impact of the neutrons knocks a proportionate number of protons out of this material. The path of the free protons is changed by magnetic force and directed down to the detecting instrument at the bottom of the tank. The detected data is transmitted by a lead-shielded coaxial cable to a distant recording station. With the thermonuclear experiment, we follow the usual scientific philosophy of covering it from as many angles as possible. We're going to study it with two additional major experiments, 10X and GANEX. 10X, the temperature neutron experiment, will measure the time of flight of the high-energy neutrons. Will detect 14 MeV neutrons using a neutron gamma reaction. The gamma rays will be collimated down through lead blocks to a detecting station similar to that used in the X-ray experiment. All of these measurements will give us enough information to prove or disprove this particular thermonuclear experiment.
A few tense hours before zero time, the network of circuits and instruments that will initiate, measure, and record the first attempt at a fusion reaction is given a final check. What is learned on Eberiru Island can have far-reaching effects on the atomic energy program. For if the correct trace appears on the face of the oscilloscopes, a new enterprise may be launched in nuclear physics.
In 15 seconds, H minus 1 minute. 10 seconds. 5, 4, 3, 2, 1, pass. H minus 1 minute. Minus 45 seconds.
from the most powerful explosion ever fired rises and continues to rise, to tower over its seemingly insignificant test island. At the last hour, George shot was changed to a daylight test because of adverse weather conditions. And we see it now, a magic ginny released from its bottle, growing larger with each passing moment, swirling, churning, boiling, a thing the likes of which has never before been witnessed. Ice caps formed and broken and formed again. From our vantage point at 13,000 feet in the nose of a B-17, the shock wave finally strikes, causes the cameraman to lose for a time that which he follows in awe and fascination through his viewfinder. Closer and closer to the symbol of 220 kilotons of energy release. Is given by RadSafe to turn away, and the George shot cloud becomes a thing of record that will live in the minds of men. Down on Iberiru, after moving up to the island 3 hours after zero time, and getting clearance from the helicopter radiological safety monitors, they re-enter their laboratory. Everyone is understandably excited, anxious to at last learn the decisive conclusions their instruments have reached. The quantity of fusible material used in this test was not sufficient to affect the fireball or produce any other visual phenomena, but they believe it was enough to be detected by ultra-sensitive electronic devices. Their answer, their success or disappointment, is inside these walls. Expectant, somewhat tense, but persistently careful hands remove the telltale film packets from the oscilloscope cameras. Even now, with the tangible, perhaps revolutionary facts in their hands, the scientists must wait until the film is couriered back to the photographic laboratory on Parry Island to be processed. The seeking minds of science know now they have produced more, much more than just another fission explosion. There is not only a trace, but a significant graphic account of the first self-sustaining nuclear fusion reaction ever achieved on Earth. It was a gamble like most scientific experiments, but it worked. With shot number 3 over and done with, work is pushed on the tower for the 4th test, the item shot on Engebi.
Since the test with the booster is a type of thermonuclear experiment, instrumentation will be much the same as that used on the Iberiru shot. Normal implosion acting upon the uranium causes fissions to occur. At the same time, heat is produced which causes the DT mixture to react. This fusion reaction, in turn, causes neutrons to be thrown out, which causes further fissions to occur in the uranium. More heat is produced, more neutrons emitted, and so on, until the fission reaction is boosted to a point where it can no longer contain itself.
Watch item shot from the ocean side of the atoll at 9,000 feet and judge for yourself. The story of Operation Greenhouse comes to a close. The semi-permanent Eniwetok Proving Ground shrinks again to garrison size. The shop is closed until the time comes when desire for further information about atomic weapons dictates another test operation. In the large frame of the atomic program, Operation Greenhouse was a soundly successful experiment. New and priceless information and statistics were secured. Previously unknown factors were established. We have learned importantly about transit times, alpha measurements, boosted fission reactions, yield computations, radiochemical results, temperatures, thermal burns, clinical and pathological findings, all of the 1,001 ramifications of the atomic idea. In the specific pattern, this is what was learned from Greenhouse. Shot number 1, dog. Shot number 2, easy. Shot number 3, George. Shot number 4, item, a twofold experiment. To determine if the DT fusion reaction could be initiated in this manner, and to study the booster effect on the U-235 fission reaction. The experiment was successful. A yield of 46 kilotons was obtained. Fission weapons proof tested. Physics experiments run on thermonuclear reactions. Offensive and defensive military and civil defense knowledge immeasurably increased. This was the accomplishment at Runnet, at Engebi, at Iberiru in the spring of 1951. Operation Greenhouse.